Hello, my name is Darcy. Thank you for coming here this afternoon. I'll be speaking about what every Java programmer should know about floating point arithmetic. Now this is an introduction to the wonderful world of floating point. And it actually is a wonderful world, because floating point is a very interesting subject. It's interesting because it takes place at a interplay between theory and practice, and between mathematics and engineering. Now, this is Oracle's safe harbor slide. There's no reason to spend much time on it because we've seen a lot this week. Instead, I want to make sure you're aware that as a visitor to the Bay Area, there are many other safe harbors you may care to visit. There's a quiet one up here in Alameda. If your interest range more on the commercial side, there's the airport of Oakland, a little more high-end Tiburon, and of course, last but not least, the city by the bay itself, San Francisco. So what is floating point arithmetic? Floating point arithmetic is a systematic approximation to real arithmetic that's useful in performing calculations on computers. Real arithmetic defines a set of values as well as a set of operations on those values, relationships between them. And floating point both approximates the set of values and the properties of the operations on those values. As an aside, I like to think there are 3 C's of technical communication: being precise, clear, and correct. And with a number of special cases dealing with floating point, often conciseness is a victim. So I'll try to follow these principles, but sometimes can only hit 2 at a time rather than all 3. An outline, since floating point is an approximation to real arithmetic, we'll start out by talking about what real arithmetic is exactly. We'll look a bit at some floating point formats and what we can do with them. We'll examine how floating point approximates the properties of real arithmetic we care about, and finally some lessons learned, and if we have some time, some Q&A. And to be, I forgot to mention, the last slide of the presentation has a link to a PDF file, and I'll also tweet that link after the talk. So you can think of mathematics as a game, and not just because your little brother or sister shows you up sometimes, but that in mathematics you're defining a set of rules, objects that live within those rules, and then as a mathematician, you work within that space to come up with results in the framework. And actually, we see this when we first start learning about math in school, even as far back as kindergarten. First, we start out with positive integers, and we just count. Now, that's not a very interesting game, so we don't stay there very long. We quickly move on to having all integers, first adding them up, and then subtracting them. Now we get positive integers in 0, along with addition and subtraction. And while this seems very basic in retrospect, it's actually a fairly sophisticated mathematical transition. What we did in creating negative numbers in 0 was to do something called completing the addition operation. Right? So we have subtraction is a partial function. If you take 2 positive integers and you subtract them, that might not have a defined answer, right? You subtract 2 from 1, there's no positive integer that makes sense. So subtraction is not complete over positive integers. So we prefer to have complete operations. So what we do in this case is make up new kinds of values that have the semantics we want. So to complete subtraction, we created 0 and negative numbers. And then we can profit or take a loss, as the case may be, for negative numbers. We don't stop with addition and subtraction. Once we have those, we introduce the multiplication operation. And since we like to be able to invert operations, once we have multiplication, then we want to have division so we can undo the operation. Now, multiplication on integers is closed, but as we know, division on integers is not. Right? Sometimes it works out well, and sometimes it doesn't. So what do? Well, we do the same trick again. We complete the function, in this case division. And the new kind of values we introduce to complete division are fractions, or rational numbers, although we still can't divide by 0. So, okay, now we have rationals, and we can divide, and we're starting to look pretty good. And actually, at this point, we have a fairly interesting mathematical structure called a field. These are the field axioms. All fields have these properties true of them, and the rational numbers are the first sort of object like this we look into. And as we can see, we do have closure under the operations in question, addition and multiplication. We have nice properties like associativity, so we can reorder operations. One context you may have seen of the field axioms like this is when people talk about compiler optimizations, because these are the sort of properties optimizers rely on to rearrange and make the expressions go faster. So it's because the underlying system, say integers, obey the field axioms that these are valid transformations. Conversely, if a system doesn't follow these axioms, then those sorts of transformations would change the value yet. You might not be valid for your system. Okay, so are rational numbers enough? Now, since we're approximating real numbers, you might suspect correctly that the answer is no. So, is there a rational number such that when you multiply it by itself, you get back 2? If we were going to express that as a polynomial, we'd say, is there a root of the polynomial x squared equals 2? Here's a little proof that it's not. All right, so let's assume the square root of 2 is some rational number. That means it's some p over q. And of course, p over q have to be in lowest terms. So we can square both sides. So we have 2 equals p squared over q squared, and then we can switch things around. And now we see something interesting. We see that p squared is equal to twice something else, right? Happens to be q squared. But what does that tell us about p squared? That means the integer p squared is even. And the only way you can get an even integer that's a square is if the thing you're squaring is even too. So now we know that p is even. Okay, so if p is even, that means p squared is divisible by 4, because it has 2 in it, so 2 squared is 4. Now we can look at q squared. Well, we've just learned that p squared equals 4 times something. Okay, so 2q squared. That means q squared equals twice something. So now by the same reasoning, q squared is even. That means q is even. Well, now we have a bit of a problem, because we've just shown that both p and q are even. And if they're both even, they have a factor in common, namely 2. Therefore, what we assumed is incorrect. We can't have a value like this, which means the square root of 2 is not rational. Now, this was very disturbing to people when this was first realized. There's an apocryphal story about a mathematician, Pacis, who figured this out. And the people he was traveling with were so upset they threw him off the boat, and he drowned. But we don't have to get that upset about it nowadays. Now you might think, well, you know, rational numbers were very good. Why do we have to deal with these irrational numbers? Maybe we can just get by without them. Well, consider something simple like a unit square, a square whose sides are length 1. It's hard to find a simpler mathematical object. Now if we want to ask a very reasonable question like, well, how long is the diagonal of that square? Well, we know from the Pythagorean theorem that it's the square root of the square of the side, so we get radical 2 even when dealing with something as simple as a square. All right, well, that's not very encouraging. So here's our first attempt at classifying the real numbers. We have the rational numbers, which are easy to understand, and then we have these irrational numbers that aren't. So we'd like a situation to deal with this. Taking roots, a polynomial seemed appropriate, so why don't we go back to our standard trick and try to get all the numbers we can from finding roots of polynomials. And when we do that, we get a kind of number called algebraic numbers. Algebraic numbers are a field too, so it seems we've made some progress. So if we want to look at the classification now, we have the rationals, irrationals. Now, luckily, all the rational numbers are algebraic. The reason is the rational numbers are a over b, and a over b is the solution of this simple polynomial bx minus a equals 0. All right, so we've classified all the rational numbers and at least some of the irrationals like radical 2. But have we got everything? Well, let's take a look. Consider this series here, 3, 3.1, 3.14, and so forth. So this is the expansion of pi, different digits. And each member of this series is a rational number, and it converges. It gets as close to pi as you want, and it's bounded above. Now, even though it has these properties, pi is not a rational number. It's even worse than that. Pi is not an algebraic number. So there's no polynomial whose root is pi as long as the coefficients of the polynomial are rational. And this is a very famous theorem called the Lindemann-Weierstrass theorem from the 1800s. And you know if people are still referring to the theorem with your name in it, it's an important result 100 years later. So it turns out pi is something else called a transcendental number. Now, again, this might be an unfortunate complexity. Can we just ignore it? If we ignore it, we can't deal with things like circles because, amongst many other things, pi relates the ratio of the diameter of the circle to its circumference. So it's a very basic property of circles. So to deal with squares, we need irrational numbers, and to understand circles, we need these transcendental numbers. All right, so we apply our trick again with a more sophisticated function, these limits of monotone series, and that gives us, as a completion, real numbers, which includes algebraic numbers and transcendental numbers. And if we had much more time, or a real analysis course, you can go through and see that real numbers, again, form a field. They have those same properties we saw before. So now the full approximation, we have rationals and irrationals are one way of looking at it, but we also have the algebraic and the transcendental numbers here. Now this figure is really not drawn to scale because almost all real numbers are actually transcendental. It's just that we don't have names for most of them. Some of the few ones we do have names for are things like pi, e, and combinations like e to the pi. Now, if you're an adventurous mathematical gamer, it doesn't stop with real numbers. There's many other things you can look at. For instance, there's complex numbers. We see these in physics or electrical engineering. In complex numbers, you do something strange. You define a square root of -1. So again, you're adding to the real numbers in that way. There are extensions to the real numbers like quaternions. These kind of fell out of favor mathematically, but are still useful for managing rotations and things of that nature. And developed more recently in the 1970s are something called surreal numbers. So surreal numbers go to infinity and beyond. They're the largest ordered field you could have, depending on some assumptions. And they were invented by John Conway, who came up with the game of life. And Don Knuth was so inspired by this work from Conway that he actually wrote a little novella called Surreal Numbers. Now, this takes place as a dialogue between a man and a woman, and it's how two ex-students turned onto pure mathematics and found total happiness. So you can kind of think of it a bit as a trans-infinite shades of gray, and that's why it has this adult rating here. So now that we've gone over real numbers, what are we doing with floating point? Again, it's a systematic approximation to real arithmetic. So how do we want to approximate? Well, not all approximations are equally good. So what are the sort of properties we'd like these approximations to have? We'd like some notion of determinism, reproducibility. All else being equal, we'd like it to be fast. If we have to choose between an accurate and inaccurate approximation, it's better to have the accurate one. And we'd like to be able to do some kind of analysis on it. And we'll look to see how the floating point approximation we have satisfies these criteria. So what does a binary floating point number look like? There's a binary significand times 2 to the exponent. So we have the bits here. And we say the floating point format has p bits of precision. And for now, we're going to assume that b0, the leading bit, is 1. We say this is a normalized representation. There's a number of reasons we do this. Makes it easier to work with. In particular, it imposes a unique representation on the numbers. So let's say you don't use all p bits of precision. If you had the b0, the first bit equal to 0, you could increase the exponent by 1 and shift everything over. Right? So there would be multiple representations for the same numerical value. So if you require normalization, then there's only a unique representation, and that's easier to work with. Because of how this is structured, numerically, floating point numbers are sums of powers of 2, with the caveat that the ratio between those components is bounded. So it's not just sums of any powers of 2 or any p powers. They have to be a limited width apart. In practice, the exponent is a roughly symmetrical range over positive and negative values. That means floating point formats can represent numbers very small, very close to 0, as well as very large, far away from 0. And the format defines the set of values based on the precision and the exponent range. So you can have multiple formats that vary just by how large they are. Now, although we're approximating real arithmetic, each of the floating point numbers is actually a rational number, right? Because it can be represented as a fraction. We can write some power of 2 that would divide this out. An important property in practice is that for a fixed width, so for a fixed format, floating point performance is roughly independent of the magnitude of the operands and the result. And of course, that's true except when it's not, and we'll talk a little bit about some of the exceptions later in the talk. All right, so now that we've had an overview of the real numbers and floating point, we're going to start playing with very much a toy floating point format. So here's a very simple floating point format that's good for slide presentations and not too much else, that only has 3 bits of precision, and it only has 3 exponent values, -1, 0, and 1. And these are all the positive values of that format written down here. So we can notice a few things. 0 is a special case, so we won't discuss how that's encoded right now. But if we look at the encodings of the other numbers here, we can see that they're all normalized, right? The leading bit is 1 for all these values. Okay? So the smallest value, which happens to be 1/2, has the smallest exponent, -1, and then it has the smallest possible significand, right? The leading bit is 1, and then the rest of the significant bits are 0. So the next larger number, we just increase the significand value by 1. So you read this as 1 times 2 to the -1, or 1 times 1/2, so we can see what the value is. Now, this position here is equal to 1/8, so 1/2 plus 1/8, and so forth. Now, we look at the values where the exponent equals to 0 instead of 1. And they have the same sort of structure. The exponent stays the same, and then we just cycle through all possible values of the significand. And we'll notice that for each setting of the significand here, it's exactly twice the value of the same setting, the significand with a smaller exponent. Right? So the first number with an exponent of 0 is exactly twice the amount of the first number with the exponent of 1. And again, that's a consequence of the encoding. Likewise, for the values where the exponent equals to 1 instead of 0. All right, so this is what we get when we have p equals 3. We can have another format where p equals 4. Now, when p equals 4, we have all the same numerical values as when we had p equals 3, except we have another trailing 0 bit. In addition, we have another set of values where the new trailing bit is 1 instead. So this has the effect of between each of the p equals 3 values, we insert another value halfway between. Graphically, we can look at this too. So here's our real number line. And we'll start graphing the values where p equals 3, starting with the exponents of minus 1. So we fill those values in. So we see those are the ones less than 1. Then we fill in the values of the exponent equals 0, and the exponent equals 1. Now, one thing to notice here is that the distance between numbers goes up when we change the exponent. So when we change exponent values, the distance between numbers is twice as much as it was in the previous exponent. And that's a consequence of the properties of encoding we saw before. Now, you'll notice here this graph, there's something seems to be missing. Right? So the distance between 1/2 and the next representable number, even in this toy format, is much, much smaller than the distance between 0 and that first non-zero representable number. So this can be a bit of a problem when doing analysis of floating point. So we actually fill in this region with something called subnormal numbers. Sub below, so these numbers have a special representation and they're smaller than normal numbers. They smooth out the set of values you have here. Now we can look at p equals 4. So again, we'd have all the p equals 3 values we had, and now we fill in the gaps between them. So we split the difference, and then we get, as a bonus, an extra number a little bit farther out on both ends. Okay? Now, the floating point numbers are imprecise. We only have a finite number of values. So we only have 16 positive values for p equals 3. So that's all we have to work with, including those subnormal values. So here we'll write them all down. So let's look at what we should do when we have to return results, say, of addition in this format. So we take two numbers in this format, 1/2 and 1 1/4. All right, so those are both numbers. And we add them together, the exact value is 1.75. Now in this case, fortunately, 1.75 is also a representable number. So that's what we should return. If we can represent the exact number, surely that's the right thing to return. Now, we're not always that fortunate, of course. How about we take something else where we have 2, all right, that's representable, and 1/8, we have that too. And the exact sum, of course, is 2 and an eighth. So we go down here, so we have 2, and then the next number is 2.5. So the exact value of this result is bracketed between two values. And it's closer to the smaller of them, 2 in this case. So it seems reasonable that we'd return the closest one. So we'd return 2, all right? How about this case where 1 plus an eighth? 1 1/8 is not exactly representable, but it's halfway between two representable values, right? 1 and 1 1/4. So what do we do in this case? Well, to guide us in problems like this, we need something called a rounding mode. A rounding mode is a mapping from the real numbers, any point on the real line, to one of the representable floating point numbers. So we'll be mapping from the real numbers to the floating point numbers. And to make it clear that we're mapping only to the representable floating point numbers, we'll take away the real number line here. So these are the only sorts of answers we can return. This is our full set of numbers here again. So let's consider what happens around a particular value, say 2.5. And our rounding mode we're going to use is round to nearest even. Round to nearest meaning that we're going to return the floating point value closest to the exact result. So starting at 2.5, the next representable number is 3. So halfway between 2.5 and 3 is 2 3/4. So that means if our exact result is between 2 and 2 3/4, the closest number is 2.5. So we're going to round down to 2.5 in that case. Likewise, on the other side of 2.5, 2 is the next representable number there. So the halfway point is 2 1/4. So if the exact result is between 2 1/4 and 2.5, we're going to round up to 2.5, which is the closest representable value. So that same argument holds for every other value there. So there's a region around each number, a little bit more, a little bit less, where you'll round to the exact value. And we can see that by looking at some particular examples. So if we take a value here, like 2 1/8, what's that going to round to? 2, right? It's going to round down to 2, right? So that's pretty clear. Now, how about a case like this, where we're halfway between 1 and 1 1/4? This is where the nearest even part to round to nearest even comes into play. What round to nearest even says, if you're in a tie, look at the two numbers that bracket the result, and the one to round to is the one with the last digit even. So if we look at 1 and 1 1/4 here, so 1 ends in a 0, and 1 1/4 ends in a 1, so what are we going to round to? We're going to round down to 1, right? And likewise, if we look at the halfway points around 1 1/2, we can see that 1 1/2 is even, so where are both of these values going to go to? They're going to go down to 1 1/2. Now, we've only done the graph out here to 3 1/2. Now, we can have results bigger than 3 1/2, so we should come up with some notion of what to do here. If we had more exponent range, the next representable number would be 4. And then we would, again, have a region around 3 1/2 that was bigger, where we'd round down to 3 1/2. So that seems to be a reasonable sort of thing to do, to add a little additional rectangle here. But that does mean that we still have an unanswered question about what to do between exact results bigger than 3 3/4 in this system. Because we have no good value here in this set of values to use to return that. So I suspect we'll have to complete a partial function a little bit later in the talk to answer that question. Some of the benefits of round to nearest even, this is the closest to kind of the grade school rounding we use, like where you 5 and up, you round up to the next value. One benefit of this little round to nearest even detail is that it avoids drift in certain kinds of summation loops. All right. Now with this toy format, we of course have rounding error when we round. We don't capture the exact value. So when we have 2 and we add 1/8 to it, the 1/8 rounds away and we get back 2. The same thing happens in the p = 3 format when we add 1/8 to 1. We just get back 1. So we just take that information away. If we look at the other format where we increase the precision, 2 and 1/8 still rounds to 2. However, 1 plus 1/8, we don't get 1 back, we get 1 1/8, the exact answer. So this is a particular instance of a more general thing we see where when we use a more precise format, we get a more accurate answer. Now, precision is a measure of how fine a distinction you can make, while accuracy is a measure of error. So to measure error, you have to have some notion of what the right answer is. And generally, using precision means you reduce your error as well, but they are separate concepts. All right, now, from what we've seen so far, this might lead us to have some concerns about how floating point arithmetic is defined. So let's say we take like 2 plus 1/4, that will round down to 2. that's fine for a single operation, but what happens when we want to add up a bunch of numbers instead? Let's take 3 numbers instead of 2. Well, in this case, we have 2 plus a quarter, so what's that going to equal? 2. All right, so then we have 2 plus a quarter, what's that going to equal? 2 again, all right. Let's say instead we add up 1/4, we add up the second 2 values first. Then we're going to get a half, and then 2 plus a half is actually 2 1/2. So this is something very important. We've seen here that floating point addition is not associative. So the order of operations matters. And we'll see more about that later in the talk. So as we've seen from the rounding slide, floating point arithmetic is only a partial function, and we need to complete it. And the property we want to have is that basic arithmetic on finite floating point values, there's always some reasonable answer. And we complete it by adding a number of other special values. We have plus infinity and minus infinity. We have something called nan, not a number. And we also have minus 0. The reason we have minus 0 is because we have both plus infinity and minus infinity. So that you want sign symmetry on multiplication. All right, so here's what the arithmetic on nan and infinity looks like. Now, nan might appear very odd, but at one point, I is the square root of -1, and negative numbers appeared odd. So it's certainly unfamiliar, but it does actually follow sensible rules. And the summary is, anytime in real arithmetic you would have an invalid situation, like 0 over 0, or the square root of -1, in floating point that returns a nan. So from the perspective of floating point, nan is not undefined. It's perfectly well defined. It's the result of these operations. Now, nan arithmetic is fairly straightforward. Generally, it tends to contaminate your result. So if you combine nan with anything else, you get a nan back. And nan has some unusual ordering properties. For any value a less than nan is false, a greater than nan is false, and a equal to nan is false, even if a is a nan. So this is very strange, but again, nan is not a number, so it doesn't act like a number in terms when you're comparing it. Infinities are a little more familiar, so if you add 2 values that are big enough, you get an infinity. So in our system, 2 plus 2 would actually equal infinity for p equals 3, because it's bigger than the limit. And likewise, if you divide by 0, you get an infinity. Arithmetic on infinities is pretty simple once you have them. If you add something to infinity, it's still infinity, and so forth. Now, once you have infinities, nans sometimes come fairly close after, so 0 times infinity is a nan. That's kind of the best you can do. And for infinities, they are ordered as you'd expect. Negative infinity is smaller than any finite value, and positive infinity is bigger than any finite value. And infinity is equal to itself, unlike nan. All right, so now that we've seen all the sets of values we have, I'll take questions at the end, in the toy system, we can evaluate floating point as an approximation. All right, again, these are the sort of properties we care about. So how about deterministic and reproducible? Well, if you look at the IEEE 754 standard, which has long been the standard for floating point, it does in detail define the results of the various operations you want. It defines the formats and the values and everything, so all this is very well defined. And if you look at the specification for CPUs, and for this purpose, the Java virtual machine specification counts as a CPU specification, you'll see something that almost always defers to IEEE 754 in terms of the definition. So if you pop open the JVM virtual machine spec and turn to the page for the d-add instruction, which talks about what to do when you add double numbers, it'll say something to the effect of, do what IEEE 754 says to do when you add up 2 double numbers. All right? So given that, why does floating point have such an awful reputation for being hard to understand if it's also well specified and standardized? Well, there's a few reasons for that. One is that those field axioms, most of them don't hold, so optimizations change the computer results. So it's not clear what's happening to your code once it gets running on the processor. There's a laxity in this language level mapping. Maybe your language specification doesn't say very much about how the language level gets mapped down lower, so you just don't know what's going on. Another issue, often library functions are not tightly specified, so you're not just using the basic arithmetic operations, you're using the math library, sine, square root, other things. Those can change. And a very important one, base conversion, decimal to binary and binary to decimal conversion. There's a lot of surprises in there that cause people to be confused about floating point. And we'll talk about all of these a little bit later. All right, so these are the field axioms again. The ones that are in orange do not hold for floating point arithmetic, so we don't have very many of them left. So we do have closure under addition, that's good. We've seen that addition is not associative, right? It matters what order we do things in. There's not even an identity element for addition, so this looks a little bit odd. The reason this doesn't work is because of negative 0. Negative 0 plus positive 0 is positive 0. And you can tell negative 0 and positive 0 apart if you divide by them. So 1 over negative 0 is negative infinity, and 1 over positive 0 is positive infinity. So while they're almost always equivalent, negative 0 and plus 0 are not always equivalent. So that's why this identity doesn't hold. So we're closed under multiplication. So we won't go through all of these. Most of these fail for a few reasons. They can fail because of round off in the floating point operations, or they can fail because of the arithmetic on the special values like nan and infinity. So if you think about what would nan do for 0 annihilation. So what's nan times 0? Nan, right? So nan is not 0, so this one doesn't work, for example. Okay. What about Java, the programming language? The Java language specification does have a few sections that talk about the floating point semantics. They're short sections. They're relatively easy to understand. Much easier for me anyway than the inference stuff that's been added more recently. And what these sections require is a subset of IEEE 754. So you have to use the IEEE 754 formats. You have to have the full set of values all the time. The subnormals, infinities, nans, minus 0, all that has to be taken care of. With one exception, you always have to use the round to nearest even rounding mode. So that's the rounding mode that's simplest that we saw earlier. And the base conversion is specified to be correctly rounded. All right, so you may have come across strict FP. So strict FP is a very minor detail that most people can ignore, but I'll tell you about it anyway. It's a subtle detail that harkens back to a time in the late 90s when there was an unfortunate interaction between the Java specification for floating point and the floating point instructions found on the x87 CPU. It was very impractical to get the reproducible results needed, so strict FP was added when you needed absolutely reproducible results, and the default FP was only slightly less reproducible. Fortunately, a few years later, this sort of concern is not very relevant anymore once the SSE2 instruction set extensions came out in the Pentium 4 and later in 2001. And this is not really relevant on non-x86 architectures. So strict FP is even more reproducible. It is required in certain instances. For example, in Java C, we use strict FP to evaluate floating point expressions used for constant folding. So the Java language specification requires constant folding, and you want to make sure that happens the same regardless of what kind of processor you're running on. Of note is that even when we have math libraries that we want to be reproducible, we don't necessarily have to make them strict FP. So it is a very limited, very specialized purpose of this modifier. So how about Java's floating point libraries? In Java, the platform, we have two libraries, Java Lang Math and Strict Math, and although they define the same set of methods, they have different specifications in each one. And there's a trade-off between predictability and speed. So in Java Lang Math, you can use any implementation as long as you meet certain quality of implementation requirements. In Strict Math, you also have to meet those quality of implementation requirements, but in addition, you have to use a particular algorithm. So this algorithm has been very stable, both over time as well as on different platforms. So this is your reproducible result here. What are those quality of implementation concerns we care about? There are two of them. One, accuracy. Accuracy of a math method is measured in something called OLPs. An OLP is a unit in the last place. And the OLP of a real number is the distance between the two floating point numbers bracketing it. So we saw before we had those discrete floating point values, so the distance between them is an OLP of something in there. And we say a correctly rounded function has an error of at most 1/2 an OLP. And what that means is you're always returning the floating point value closest to the exact result. And that's really the best you can do. Right? If you're returning the closest value, what more can you ask for? Now, most of the methods in math and strict math don't have a 1/2 OLP error. Instead, they have a 1 OLP error bound. What that means in practice is that you can return either of the floating point numbers which bracket the true result. Now, often just that gross error bound isn't enough to be useful. We need something called a semi-monotonicity requirement. Often it's important to approximate the properties of a function rather than just the values. So an important property is that when the function's increasing, we want the floating point approximation to be non-decreasing. We don't want it to go down when the function's going up. So it can either stay the same or go up. We might not always be able to have the floating point approximation go up because we might not have a number we can use there, right, while still meeting the accuracy requirements. So we'll see what this accuracy requirements looks like with the square root function. So here's square root on the toy equals 3 range. So we'll notice a few things about it. It's non-negative, right? All the values are above 0. It's nice and smooth, and it's monotonically increasing, right? So it's always going up. So here's what the error, a 1/2 ULP error bounds around square root look like for the toy format. Now, the size of an ULP changes at an exponent boundary, and here are the toy values from before. So, and then this is an ULP with a result. So we can see here when the result is less than 1, the ULP is smaller, so that corresponds to these narrow boundaries. And then when we go above 1, the distance between numbers double, so the size of the ULP doubles. That's why we have this jump up here. All right, so now we have 1/2 ULP and 1 ULP bound, so the 1 ULP ones are twice as big, as you'd expect. And at first, we'll look at a not so good approximation to square root. So this is a version of square root that meets the 1 ULP error bound. And it does exceed the 1/2 ULP error bounds, so it's not that good in that way. But it also has this semi-monotonicity requirement here, right? So between these 2 points here, the true square root function is increasing, but unfortunately our approximation is decreasing. So we wouldn't want to use this approximation if we could avoid it. We'd much rather use an approximation that looks like this. So this is the correctly rounded approximation to square root in this format. We can see, we can see that it has the semi-monotonicity requirement. It's either going up or staying the same, and it meets the error properties. So this is the best we can do for a square root approximation in this format. Now, while it's easy to see what's going on with square root looking at it graphically, that's not the only way you can think about it. You can also think about, the 1/2 ULP is a bound. Sometimes you have an exact value, so there's no error, and other times you do get very close. But this graph is not the only way you can think about floating point. You could also think about the square root function as this table. So these are all the different floating point values in this format. We have all the negative ones, we have the positive ones, and we have the special values. And we have the value of the square root for each of these values. So this is all the information about the toy square root function. This is it. That fully captures it. A very important aspect of floating point is that while real arithmetic is continuous, floating point arithmetic is fundamentally discrete. You can think of it as a table like that. That's all the information about the square root function. Another important thing is a floating point number only represents itself. Without any other context, you don't know where the floating point number came from. As we saw with the rounding example before, maybe you got the floating point number and it was exact. Maybe you got the floating point number and it rounded down from something else. Maybe it rounded up from an exact value. You just don't know without any context. So if all you have is a number, the safest thing to do is assume it's exact and go on from there. Because of this discreteness, from a certain point of view, things like floating point addition is just a big lookup table. Now, we don't just think of it that way because we want to use the correspondence with real arithmetic to aid our comprehension and to help decide what the right answer is. All right, so we talked about these toy floating point formats. What do the real floating point formats look like? Well, they're a lot bigger. We have the float format that's 32 bits, 24 precision bits, 8 exponent bits. It has a range in binary and decimal. The double format's bigger, 64 bits, much larger precision, larger exponent range too. So double can represent values that are both much smaller in magnitude and much larger in magnitude. Now, while these are the exact binary values for the formats, people like to think in decimal. So what are the equivalent decimal values in terms of the decimal digits of precision? It's a little complicated because the relative precision of binary and decimal varies at different regions. So for float, it's between 6 and 9 decimal digits, and for double, it's between 15 and 17 digits. All the float values can be represented as double because of the way the formats work. And here's a fun fact. Over 45% of the double numbers are actually numerically integers. So why is that the case? Well, what happens when our exponent is greater than the number of precision bits we have? Can any of those significant bits be fractional? They can't. Say if you have an exponent bigger than 54, you know that all the bits in that significand are some kind of integer. So floating point shouldn't be too hard to understand because it's almost half integers. One reason you might think that double is twice as big as float, but that's not the only way to think of it. Because of the increased precision, between two any representable float numbers, there are about 500 million double numbers. So that means the ULP of a particular value as a double is 500 million times smaller than the ULP of a float. The error bars are 500 million times smaller. And it's highly recommended to perform computations in double instead of float for that reason. Because you have so much extra precision, the likelihood you'll run into a numerical problem is much, much less. All right, with that, we'll talk a bit about decimal to binary conversion. While integers can be exactly represented in any base, the fractions you can represent depends on the base. And the example we've seen from grade school is that in base 10, 1/3 is a non-terminating expansion, right? 0.33333. How about in base 3? In base 3, 1/3 is nothing special. It's just 1/10, right? So it's 1 times 3 to the minus 1, right? So we see here that it's a property of the base. And many of the floating point sources of confusion are related to decimal binary conversion properties, all right? So why don't we try to convert 1/10 to a binary fraction? All right, well, we'll start the conversion algorithm going. You multiply by 2, you take the leading digit, you keep going. That's all fine. And then we notice, wait, we have repeated state between here and here. So if we keep going, we're just going to loop through these values. What that means is that 1/10 in decimal is a repeating fraction in binary. Just like 1/3 is a repeating fraction in decimal, 1/10 is a repeating fraction in binary. Now, let's see, yes. Let's look at the other direction, going from binary to decimal. Initially, this looks more promising because all terminating binary fractions can be exactly expressed as decimal. The intuition is that 10 equals 2 times 5, so all the fractions in base 2 or base 5 can be represented in base 10. And the proof is kind of along those lines. So 1 over 2 to the k is 5 to the k over 10 to the k, right? So 5 to the k is just some integer, and if you divide by 10 to the k, you're just moving the decimal point. So there's nothing that can cause a non-terminating fraction there. And since binary floating point numbers are just sums of powers of 2, and the powers of 2 are either fractional powers of 2 or integer powers of 2, all the powers of 2 can be converted to decimal without a problem. Now, what would happen in practice if we wanted to use this exact decimal representation of the floating point fraction, right? If there's an exact representation, maybe we should try to use it. All right, well, let's start looking at what happens when we convert, negative powers of 2 to decimal, 1/2, that's looking okay. But this is starting to get kind of long. So the smallest number we have in double is 2 to the minus 1074. So let's look at what the exact decimal representation of that looks like. So it starts out 4.94 and it goes on for a while, and it's actually not done here. It keeps going and it's going some more. Okay, so even without the leading zeros, which we've left out, there are 751 digits in this digit block. So that's a little awkward to work with. If you wanted to print out a value to have like a format specifier, you need like a whole page to print this out. So we don't want to do this. We want to do something else instead. So if we want to step back, what are the properties we want to preserve? Well, if we have a round trip like this, start with binary, convert it to decimal, and convert it back to binary floating point, we like to recover the original value. That way we can use text for information interchange. We don't always have to use a binary format. And to do this, the exact value is not necessary. We know that the decimal to binary part has to deal with imprecision in rounding. So the approach is we'll use an inexact decimal string for output, but one with enough precision that we can recover the initial value. So now, as we've seen, there are many values that will map to the same floating point number. So that means there are many decimal strings that represent potentially the same floating point value. We have that whole region around a number that will round to it. So there are multiple strings, for instance, that would round to a floating point value equal to 1. So we could have 1.0 as well as 1.000 and so forth. So which one do we want to choose? Well, how about the shortest one? That seems reasonable, less output. And this is actually a general trick used in mathematics. When there are many possible answers, in this case an infinite number of answers, if you impose enough side conditions, you can get a unique answer. And often having a unique answer is easier to deal with than having many answers. Right? And yes, we've seen before, multiple numbers go down there. So how long should this value be? Well, it depends on the format, so it is a function of the format, and it also does depend on where you are in the range because of this floating precision problem or between binary and decimal. All right, so if we have the binary to decimal conversion, we use the shortest string for that, and that's generally inexact. Then we have the decimal to binary conversion, and that's inherently inexact. But by being careful, this composite function is actually the identity function. So we take two inexact processes and we get an exact process back. So that's kind of cool. And the takeaway message here is when you see a decimal floating point string, think of its nearest binary neighbor instead. Now you might say, well, this is all very complicated dealing with decimal strings for binary floating point. Is there something else? Yes, there is, although you might be forgiven for thinking that the cure is worse than the disease. There's actually hexadecimal floating point literals. These were added to the revision of the IEEE floating point standard, and they've actually been in Java since JDK 5. Now, the structure of the floating point number is that you have a significand and your exponent, and there's a textual representation that matches that basic structure. So you have a hex significand and then an exponent. So the advantage of hexadecimal literals is that it's somewhat human readable. It's obviously unambiguous, and it can be tied to the format. So we'll just do a quick example here. Let's say we want to represent the number 3.0 as floating point. One way to write that as a hex literal would be 3 times 2 to the 0, so 3 times 1. Now, that doesn't match how it's stored in the floating point number. A way to do it that matches how it's stored would be this 0x1. So this is the normalized representation, so the leading bit of 1, and then 0.8. So 0.8 in hex is equal to 1/2, right? So it's the leading bit set. So this would be 3 times 2 to the first, which equals 3. So this is how 3.0 is stored as a floating point number. All right, so now we have enough background to understand some of the initially surprising results we see in floating point. So for instance, why is 0.1 as a float not equal to 0.1 as a double? Well, if we print out the hex strings for 0.1 as a float and a double, we'll notice that the double version is much longer. And that's, again, because 0.1 is a repeating fraction in binary, so when we use a format with more precision, we get more bits of the approximation, and because between each float number we have 500 million double values, this value as a float is very far away from the other double numbers in this range. So if we look at the exact value of the float approximation for 1/10, we get a number that's close to 0.1, about the leading 8 digits are correct, so that again matches the precision. But when we use a 0.1 as a double, we get a much better approximation. Instead, we have leading 17 digits correct. And if we take this float value and print it as a double, we'll again get something that matches to 8 digits, but it's pretty far away from the exact double value when you consider the double format. All right, so let's say you add up 1/10 to itself 10 times. What do you get? Well, it depends. So if you take a simple sum like this, where you just add 1/10 to itself, and then you just keep accumulating that sum, if you print it out at the end, you will not get 1. You'll get the biggest number less than 1, 0.99999. So if you look at the exact value of that, it has an error about 1 part in 10 to the 16. Now, we've discussed, and you'd expect to get 1, or you'd hope to get 1. Maybe that's not fair, though, because we've discussed that 0.1 isn't exactly equal to 1/10. It equals this other binary value. So if we assume those binary values are exact and add them up without rounding, we get this value here that's slightly bigger than 0.1. And if we were to take this value without rounding and then round it to double, we would indeed get 1 back. Let's say we decide to add things up differently. Let's say we add up pairs of values and then pairs of pairs and so forth. What happens when we do that instead? In that case, we do get 1. So this is another instance where the lack of associativity of floating point arithmetic is showing up. We do the operations in a different order, and we get a different answer. In this case, we get a better answer. So once we know we can get a better answer by doing things differently, the question is, how do we get those better answers? Well, there's a few things you can do to get a more accurate sum. You can sort the inputs. That takes extra time, of course, and extra space. And you can add the small magnitudes to each other first to reduce round off. You can use more intermediate storage. This pairwise methods end up using more intermediate storage. And you can also use higher precision for intermediate results. So you can kind of catch the rounding errors in the middle and have a single rounding error at the end. And now you too can enjoy the benefits of the secret robot internet based on this talk. How about speed for the approximation? There's a very good hardware support for normalized floating point values. Add, subtract, multiply tend to both run in not very many cycles, say less than 7 cycles, and be pipelined. So every other cycle or so you can issue a new one. So here are some particular numbers from a recent x86 architecture. Divide is much slower though, so it tends to take a lot longer and not be pipelined. So these are representative of what you find in mainstream processors today. Now, what about other values like subnormals, nans, and infinities? The picture there is less rosy. It varies more. The operations can be made fast with some modest additional hardware inside the CPU. CPU designers don't always choose to spend their hardware resources that way, however. Arithmetic on nans and infinities is very simple. We saw most of it on that slide where we introduced nans and infinities. So it really is just a little bit of extra area to make nans and infinities go fast. Subnormals are a bit more work. But it is important to point out that the representation used inside the FPU doesn't have to match the format that's used in the floating point registers or when you store the numbers. So you can partially decode the numbers to make them go faster. How about accuracy? Well, we've seen here we have 2 formats. The double format has much higher accuracy. We can make very small distinctions here. So if we look at an ULP of 1, so what's the distance between 1 and the next representable number? For float, it's about 1 part in 10 to the minus 7. Double's much smaller, 1 part in 10 to the minus 16. This is the same sort of effect we saw with the toy formats, where the distance between numbers is much smaller when you have more precision. So at a micro level, this all seems to be not so bad. If we start looking at the operations, the basic operations are all correctly rounded. So if you assume the inputs are exact, you get the closest floating point value to the exact number, so that's good. Now the hard part comes in when you have to move away from individual operations and look at kind of what's the global error. So this is actually hard, and you might be relating your discrete floating point numbers to some continuous process in the real world, and that's difficult. And numerical analysis is a very venerable, if rarely loved, subdiscipline of computer science. So how many people have a CS degree and didn't take any numerical analysis classes? Did not. Okay. How many people, raise your hand then if you have a degree with or without CS, or with or without numerical analysis. So. Yes, it used to be mandatory. I think it's getting less mandatory as time goes on. One thing, we can actually synthesize higher precision operations out of standard arithmetic. And the reason we can do that is that the rounding errors are correlated. They're not independent. And if we know exactly how big the error is, we can get rid of it. So we don't have too much time left, but I'll just quickly put up this slide here. What this series of additions and subtractions does is, given A and B, it finds the high order bits of the sum of A and B. And in addition, it includes all the trailing bits as another word. So x and y don't overlap at all, and they represent the exact sum of a and b. And we're able to extract that because of the rounding errors are correlated. So this is the sort of kernel you might include in code that implemented higher precision in floating point. Now, as we've seen before, simple sum can have very disappointing numerical behavior, as we saw with all those values kept rounding away when you added them to 2. There's another technique called compensated summation that has a much smaller worst case error bound. And it's implemented using a similar technique to the one shown on the previous slide. You have the sum contained in 2 doubles instead of 1. You have the higher bits of the sum, and then you have a running version of the error bound. And we use this technique in the new streams library in JDK 8 to help make sure that the sum you get back is numerically pretty good. It does run somewhat slower, but it is much safer than just doing the simple summation. Now we can go on to a few of the lessons we've learned. The main lesson to take away is know when to expect exact results in floating point. Being confused about that is where most of the problems come from. And by default, you should not expect your floating point results to be exact because you're having all those rounding errors when you do operations. There are some conditions, though, where you can expect exact results. In the double format, we can represent all the contiguous integers between 2 to the 53, minus 2 to the 53, and 2 to the 53. So if you're operating on integer values that happen to be stored as floating point numbers in that range, because of correct rounding, you'll get an exact result. So if your integer valued add or multiply operates in this range, you'll get the exact value in the floating point. That's fine. If you're doing operations on powers of 2, since that works well with the binary floating point, again, you can expect to be exact there. The special algorithms for extending precision, again, you can expect to be exact. And certain cardinal values of functions, like sine of 0, should be exactly 0, not even a very small value. Now, you should be cautious with money, probably in general, but especially with floating point, because you can run afoul of some of the problems we've seen, such as the decimal to binary conversion issues. So you can't necessarily represent your fractional dollars or pounds or euros as a double value, so you can get error there. So if you're doing that, instead you should consider using an integer type, and instead of dollars representing cents or mils or whatever the smallest unit is, and multiplying up so you have an integer value. Now you can do that sort of computation as an integer type, and you could also do it as a floating point type as long as you paid attention to those range limits where you can represent all the integers. When you really need to use decimal fractions, use big decimal. That's what it's there for. Big decimal holds decimal fractions exactly as well as decimal integers. Now, corollary of exactness is checking for equality. Again, unless special circumstances hold, it's usually a bad idea to check floating point numbers for exact equality unless you know they're exact. You can check against 0 to avoid divide by 0, but you should be warned that if dividing by 0 is bad, dividing by a very small number probably isn't very good either. So you might want to be careful there. So here's the sort of thing that can happen if you have a unfortunate equality check. So this is actually an infinite loop. Right? You can see why from before, right? If you keep adding 0.1 to itself, it's never going to exactly equal 1, and you just keep flying past the value. And actually, eventually it'll stabilize and not get any bigger, so it won't be very interesting. So instead, if you want a counted loop, if you want to add 0.1 to itself exactly 10 times, have the canonical loop from doing something 10 times. If you want to look in the floating point domain, say you're waiting for some kind of root find to converge or something, use an ordering comparison like less than or equal to, so you don't blow past the limit. All right. For trig functions, there's not very many cardinal values. Just very quickly, so you might initially be surprised that math.sine of 180 degrees is not exactly equal to 0, and sine of math.pi is not exactly equal to 0. So is there a bug in the sine library? No, this is not a problem. Pi is transcendental, so it can't be represented as a floating point value, and so it's not exactly equal there, and I've been giving a hook. Just briefly, in the Java platform, we have very strong semantics around floating point. The language specifications and the VM specifications have always been very explicit, defining the floating point semantics at both the language and the class file level. If you're using other languages in the Java platform, either that compile the class files or to other object-compliant CPUs, you may not get the same sort of guarantees. So be careful there. There's some other references if this hasn't totally exhausted your interest in floating point. And since time's up, I'll be happy to take some questions informally up here. All right, thank you.